Hi, my name is Sylvia. Today I'm going to be talking about some of the work that we have going on in my lab. I'm not going to be talking about all of it. I do want to quickly highlight my lab, which has grown very quickly since starting at the end of 2020. I have wonderful PhD students and undergraduate and master students, and they're working on a range of projects. I want to quickly mention things that I won't be talking about today in case anybody wants to meet up later. So we do a lot of work on this thing called reachability theory. I'll go into it a little bit more. Safe reinforcement learning using iterative reachability estimation is something that we've been working on. Something called Koopman-Hopf reachability analysis for fast and scalable nonlinear reachability approximations, where we can, for example, drive this 10D glycolysis model, the ATP levels, up to desired values very efficiently. Advances in reachability using system decomposition and handling noise and partial observations. We also have some work that's just more generally control and machine learning, reasoning about safety when interacting with uncertain environments. So for example, debris, aka Pringles cans, that you need to move around to get to a goal while hopefully not knocking them over, and you have to reason about this online. Continuously trading model error with planning speed. So how can you get away with as much error as possible such that you can still make your way towards the goal? Conformal prediction and temporal correlations for reducing conservativeness in pedestrian predictions while maintaining safety. And some control theory applied to policy gradient methods, identifying when the optimization landscape in the control policy space is very non-smooth or fractal using control theory. I know that was very fast, but I just want to give a quick highlight on some of the other directions that we're doing that I'm not going into today. Today, I'm mostly going to talk about this, value functions for safe control, where the basic idea is that we want to be able to take our state space and define a value function over this state space that takes the desired safety constraint and the long-term effects of the dynamics of your system and composes that into a single scalar function. So if I query a particular state, it tells me by the level of that, the measure of safety. So if it's positive, safe, negative, unsafe. And the gradient tells me the safe direction. So it informs the constraints for my safe control. This is the basic idea of what I would like to use. We use these online for something called safety filters, where you say, I want as much as possible to follow the direction I'd like to, subject to maintaining these safety properties with respect to this function. There are two communities that use this a lot, potentially, I guess, more, but two of the ones that I see a lot right now are control barrier functions and Hamilton-Jacobi reachability analysis. I'm from this background, which I'll get into in a minute. And when I was interviewing, I was asked regularly why I wasn't just using control barrier functions. And I wasn't really sure, honestly, what the answer was, so I made up some things. And then when I started my job, I figured I should actually dive into this and see what is the relationship, because both of these are ultimately trying to find that function that I showed on the previous slide. So my very quick summary is if I split this up into the initialization of how we find these functions, the construction of how we develop these functions, and then the use of how we use these functions online, control barrier functions are very similar to control Lyapunov functions. They're essentially upside-down Lyapunov functions, and they come with all of the challenges of finding a control Lyapunov function for a nonlinear system. And so for initialization, there's ways to hand design these for very certain types of systems where you can then find an analytic function. And it's very popular to do data-driven approximations. They're trying to construct these just from data that tells you things that are safe and things that are not safe. But for construction in general, there's not a method for general nonlinear dynamic systems with control bounds, potentially disturbance bounds. There's no general constructive method for this. On the reachability side of things, we typically initialize with a signed distance function to obstacles or failure. And then we do just brute force dynamic programming to that. So we encode, given the dynamics of our system, what trajectories will end up inside high cost areas and which ones will maintain low cost. Doing brute force dynamic programming means that we have a very slow but rigorous method of constructing these functions. They have general systems, input and disturbance bounds, provides the maximal safe set, et cetera. And then for use of this in reachability, we end up with an optimal safe control, where it tells me that the change in value, my change in safety over time, will always be greater than or equal to 0. This means that If I start at a particular value of safety, I must be monotonically increasing in safety. So that means that you're constantly moving upwards or at the same level of your safety function. This is very conservative, to be always running away from obstacles forever. So instead, what we use in reachability analysis is something called least restrictive control, where we set that threshold to 0. When you're above that threshold, when you have a positive safety value, do whatever you want. As you approach the boundary of that threshold, you override it with this optimal safe controller. This is nice in that it's least restrictive, but you can end up with these very choppy looking trajectories. So how we typically use this in reachability analysis can either be very conservative and or jerky. In practice, people often do some sort of averaging heuristic between the two, but not very principled. The control barrier side of things uses this control barrier function quadratic program, which is a QP for control affine systems. That's saying minimize the control effort such that you obey this safety condition, where now instead of v dot is greater than or equal to 0, it's greater than or equal to this minus gamma v. If I plot out that minus gamma v, that's going to be this curve here. And so what we're saying is that your safety value must stay above this curve. So when you're very safe, you can decrease quite a bit your amount of safety. As you approach the boundary of safety, where safety approaches 0, you must stay above that boundary. So this is a kind of a nice way of trading off between being less restrictive when you're well inside the safe set and more restrictive when you're near the boundary. It's often called like the smooth braking condition. So you can have these nice, smoother trajectories that gives you fast analysis and nice trajectories. Okay, so that's kind of the very quick high-level summary. Once we looked into this, we then asked, well, can we smush these things together? So can we take all of the work being done on trying to construct approximations for control barrier functions, apply some minimal, hopefully, rigorous dynamic programming to them, and then online use this nice QP to trade off the controllers? So that's what I proposed in this ONR YIP. So can theory and tools from Hamilton-Jacobi reachability be used to construct the best control barrier functions? Next, can tools for quickly approximating control barrier functions be used to initialize that reachability? Rather than starting from that sign distance function, can we start from something that's very close to the true function? And then finally, can we update these functions online based on changing assumptions and information? The last one I'm going to mention is, how can we reduce conservativeness for unmodeled dynamics? And I'll give the motivation for that soon. I'm hoping to spend most of my time on this and this. So first, for the theory and tools to smush them together, I'm not going to go too far into the details, but the answer is yes, we can. So in reachability analysis, the dynamic programming that we do uses something that's very similar to the Bellman equation, but for a continuous time and space. It looks a little bit more intimidating, but this is our update that we do. You can think of this as the Bellman equation. The result from this encodes this v dot is greater than or equal to 0. We realize that if we just modify this Bellman equation by just adding that term that we want to show up into the constraint, that gamma v, when we go through the process, we end up with 0 is greater than v dot plus gamma v. So we embed the constraint that we want inside of our construction of using dynamic programming. So we end up with v dot is greater than or equal to the minus gamma v. This allows us to obey that CBF QP constraint with that rate gamma that makes that curve. And so we can construct a CBF-like function that encodes control and disturbance bounds and the maximal decay rate that you want. A quick peek at some of the highlights of this work. So here we have, let's say, a goal, and we have just one obstacle. And I'm showing the boundary of this safe set. So you're safe when you're outside, and you're unsafe when you're inside. And I'm showing a slice at the current orientation of my robot here. If I just use my safe controller, it's going to run away from the obstacle. It knows nothing about the goal. It's just trying to move up the value of safety. If I do the least restrictive control instead, only activate the safe controller when you're on the boundary here, then I end up with something that looks like this. Great, I reach my goal, but this is what my control trajectory looks like. If I then instead use the CBF QP, I reach my goal, and I have a much smoother control signal over time. We also, using this, can look into other benefits of using Hamilton-Jacobi reachability, like reasoning about infinite time versus finite time safety. So here I have an example where there's a goal and two obstacles, and these are the unsafe sets. And if I want to guarantee infinite safety, I cannot reach this goal. So if I try to reach this goal, it gets pushed away, because if I reach this goal, based on my dynamics where I can't stop, I will inevitably end up hitting the obstacle afterwards. If, say, you have, say, a hybrid system where once you reach a particular goal, you switch into a different state space, and so you don't care about what happens after you reach the goal, then we can consider finite time safety. So only be safe up until you reach the goal. And then we can actually encode that into the construction of this function. We've also flipped this around. I mentioned that control barrier functions are upside-down control Lyapunov functions. And so with some pretty minimal changes to the theory, we're able to construct control Lyapunov-like functions, where for systems without control, we can conservatively estimate the region of attraction. So here's a region of attraction for this system. And here is what the reachability analysis produces for us. For systems with control, we can conservatively estimate the region now of exponential stabilizability given a desired decay rate. So if you want to reach a particular goal with a very high rate, a very aggressive rate, then there's a smaller region from which you can reach it than, say, if you use a less aggressive rate that you want to reach the goal by. And we can, given the different rates that you want, we can encode what the appropriate function looks like. And then for systems without an equilibrium point, where you're not just stabilizing to one point, we can stabilize to the smallest control invariant set around the origin. So here for a Dubin's car, a car that's at a fixed speed where it can't stop, so there's no equilibrium point, its tightest set is one in which it's doing donuts around the origin. And we can recover that you get this set and you can stabilize down to that donut. So we just presented this in ACC. And that was my very quick, high-level introduction to the background here. So now we've figured out this step. And now we've started expanding into, now can we use tools from control barrier function community in order to efficiently initialize this. And this was led largely by my student, Sander, who's coming to me from his master's with Marco. So thank you, Marco. The motivation here is something like this paper from my colleague, Sean Gao at UCSD, where there's a lot of interest in developing these data-driven control barrier functions. So you gather a bunch of trajectories, information on what's safe and unsafe, and you try to fit, using a neural network, that function that encodes positive is safe, negative is unsafe, and the gradient points you in the direction of safety. This is great because it's much more scalable than doing brute force dynamic programming, but you end up with regions that do not satisfy all these constraints. When you use those regions as counterexamples then and continue training, then you refit your function and test again. And eventually you may get to a point where each time you refit to your function, you may recover safety for those initial parts that were unsafe, but introduce new regions that are now unsafe. Because of each time that you fit it, you get something slightly different. So eventually you may get to the point where you have something like this. In this paper, all of the green trajectories stay safe, and all the orange trajectories highlight the regions where the barrier was leaky at the boundary of the safe set. People from formal methods, like my colleague Sean Gao, can identify the regions where they can formally guarantee this and the regions where they cannot. And so can we use that information to seed our reachability analysis, that painful dynamic programming method? So enter my student Sander. Here he shows an example where he's using one of these data-driven control barrier functions as a safety filter. And he, for example, if you're trying to reach this goal, this particular function is too aggressive in its safety, so it keeps you from being able to reach the goal. If you want to reach this particular goal, you actually end up violating safety here, so that function was invalid, the safety filter. If we use that as our initialization for Hamilton-Jacobi reachability, we find that if we start with a set that's too conservative, a function that describes a safe region that's too conservative, each iteration will maintain or improve the conservativeness. If we start with something that's unsafe, each iteration of reachability will provide something that is safer. So when he plugged in that data-driven control barrier function, and we did this analysis, and we continued to operate the dynamic programming until convergence, we ended up with a safety filter that did this, for example. Managed to maintain safety and also increase performance compared to the original approximation. So he presented this at IROS last year. The initialization can come from, for example, an analytic CBF for a different problem formulation. So for example, one that has no input bounds or slightly different dynamics or a constraint set. It can come from an invalid control barrier function that's paired with a backup control policy. This is something that's popular in the CBF field, where if you have a function that you know is wrong, if you have some backup policy like break early because you know that the function is wrong in these regions, then you can kind of slap that backup policy onto in addition to your safety filter. We can actually now embed that policy into the construction of the function itself. And it can also come from data-driven control barrier functions. This is nice. The convergence is much faster than with standard Hamilton-Jacobi reachability because we're starting with something closer to the true solution, but each iteration is still over a global grid of the state space. So in this particular work, we are still updating everywhere at every instant in time. And so it still was a very tedious process. So now we're asking, well, again, Sean was able to show, in these regions, everything's fine. And maybe in these regions, I don't really care that much. It's not on the boundary of safety. The important regions are really around these areas that he's identified being leaky. So our current work is on taking one of these approximations along with that information of what cannot be certified to be guaranteed to be safe. In this example, here is our function, and here is the 2D slice at 0, where you go from safe to unsafe. And we're highlighting the points that Sean's students cannot guarantee obeys the CBF constraint. We then use reachability analysis in this region locally and reason about what regions of the space need to be active currently and need to be updated. And we adjust the function and the corresponding 0 level set accordingly. Doing this, we can either find the barrier function associated with the trained neural control policy. So if you trained a control policy, you don't want to modify it, and you just want to know what is the region in which this control policy is safe. We can identify that. Or if you're willing to let us mess with your control policy, we can then tweak it at this boundary and say, really, you should override your policy and use this in this region, and you can maintain safety better. So we can update the control policy along the boundary to find the control barrier, we call it value function, with the largest safe subset of the initial safe set approximation. Here's a slice of the data-driven control barrier function. The safe set in green, again, are the trajectories that maintain safety, and red are the ones that did not. Here's what happens after we patched it. Notice that we do have still a few trajectories that end up leaving. We believe that this has to do with the density of the grids that we're sampling. And so we have to do some sort of adaptive sampling method in order to reduce these trajectories that leave. In terms of rolling out these trajectories and looking at what's safe and unsafe, if we just use the neural nominal policy that's used to train that barrier function, so we use the same control policy that's used to make the barrier function, then both are fairly safe, but still our patched one is safer. If we use a different control policy, just LQR, if you're just trying to get to a goal using LQR and you're using this as a true safety filter, then the neural CBF is much, much worse. It's really just directly paired with its particular control policy. Our patch CBF is much better. This local patching is approximately 2 orders of magnitude faster than the original refined CBF work, where we updated the entire grid. I say approximately because it really depends on how good that initialization is. If it's really good and we have to just tweak it slightly, then that's great. In practice, finding these data-driven CBFs is quite hard, and there's many, many regions that end up being questionable that we have to deal with. So that's what we're exploring now. And then the next plan is, can we update these online based on changing assumptions and information? This is now the next step for Sander. I've pointed him towards doing experiments. We're just now starting to, he has, one master student over the summer started getting our ROS platform up and running with our motion capture to start some initial stuff. We're now expanding into using more vehicles, aerial vehicles, et cetera. We're also starting collaborations with Nikolai Atanasov and Jorge Cortez, because all of my work up until now has assumed perfect state information. So assume that I can instantaneously get exactly the information about the state of my system and the state of the obstacles in the world. Fortunately, I sit right next to professors that do not do that. And so we're going to incorporate with their work on control barrier functions that are robust to measurement errors in the perception-based navigation. And then Sean and I are interested in applying this to Henrik's robots. So Henrik is the director of our Robotics Institute, and he has this fleet of both ground robots, aerial robots, but also golf carts, autonomous golf carts that he wants to drive around campus and not hit students with. And he said that if we get this working, then we can try playing around with not hitting students, hopefully. And so we're very excited about moving into this direction. The problem is, when you're dealing with people now, you have to deal with either how do you model these people, right? In control, we typically assume worst case analysis, so assume that all humans might be trying to run at you and throw themselves in front of you at all times. On the learning side of things, we typically just do a bunch of training and then hope that the people online in the real world behave the same way as the people in the training. And so how do we deal with modeling humans? You have a question?
If you hit a student, do you have to pay their tuition?
That's a good question. I have no idea how Henrik gets away with this in terms of the IRB and all of that. So that's a lot. Oh, that's my screensaver. That's a lot of why I am eager to just hop on board and let him handle this stuff. Anyway, okay, so this is what I kind of mean about, and I'm coming from the control side, so I'm used to doing this worst case modeling, and I really don't want to deal with that conservativeness, because then you end up with the freezing the robot situation where it's afraid of every single person on campus and doesn't move at all. So yeah, this is the motivation. You have a robot, you want it to be able to get through to other people. One thing that we do in controls using these safety functions is that we consider pairwise collision avoidance. So we'll just slap down one of these functions on each human that just says, okay, what are the safe actions that will avoid entering this unsafe set with respect to this one, this one, this one. You consider them completely independently, and then you say, I want to minimize the difference between my desired control subject to obeying the safe actions with respect to each person. Note, you can also take the pointwise min to make one CBF, though you may have some differentiability issues. There's a problem, though, with doing that. So analytical or dynamic programming-based control barrier functions for pairwise collision avoidance tend to assume that the actions of other agents are all equally likely. This is the worst case analysis that I mentioned. So, if I'm assuming that any human might go anywhere at once, then I have this huge unsafe set, and the robot has to take very, very conservative behavior. Data-driven control barrier functions, the stuff that Sean's dealing with, are very sensitive to the training environment and may not be representative in other environments. So as an extreme illustration, let's say you trained in an environment with just one person, and so you ended up with a safe set that pretty much said just don't go in front of the person. They tend to walk in straight lines. Now, if you were to test on an environment with two people, Now you assume that these people are completely independent and therefore can walk through each other. And so the unsafe sets will look something like this. And you say, great, they will walk through each other, and I can take this trajectory right nearby them. And clearly, we did not capture some of the interaction effects that happen between humans by training on just one. Again, extreme example, but to illustrate. So the core issue here is that I want to maintain these independent control barrier functions for scaling reasons. Being able to just see a human, slap down a function, see a human, slap down a function is great because I don't have to think about their joint dynamics and reason about the joint state space. But I also want to encode interaction effects, which kind of seems like by definition you have to reason about joint things. So are these two desires completely at odds? I thought yes. Sean said no. And he proposed this idea. So let's imagine that you're this robot in this dense environment. You know that it's a dense environment, but you're only focusing on one person. And you see that they're moving. And you reason, can I safely move forward given how they're moving? Well, yes, probably. They're going to keep moving straight. If instead you see that this person suddenly makes a turn, knowing that you're in a dense crowd, you could probably infer that they're making this turn because there is some interaction effect that's happening with another human, and therefore taking that path is not safe. Instead of explicitly doing all this reasoning, if we trained in an environment with multiple people, then we could encode these interaction effects implicitly. Just by crashing, when you crash into the second person and you mark that as unsafe, you eventually learn that when this person moves this way, you probably shouldn't move straight. So the idea is train in an environment with multiple agents, but only measure the current and a little bit of history of one agent. Keep track of what actions lead to collision versus safety with anybody, and use this to train a pairwise collision control barrier function. We call this idea a sequential neural CBF, where the training procedure now is we're going to use trajectory samples to get a rough landscape of the control barrier function. And then we're going to resample around the boundary of the safe set to refine it. And I'll show you what I mean by that in a second. So the training procedure is we have a loss function that encodes that, first, the value of safe states should be positive. So this penalizes if the value of certain states that are safe is negative. We're here, this is the agent state, this is the human state sequence, and this gives us an error margin. So I sum this up over all of the states that are in the safe set and ensure that if any of them are marked as negative, that's encoded in the loss function. Vice versa, the value of unsafe states should be negative. So now we have that we're summing over the unsafe set, and we took out the negative sign here. And then finally, the gradient should obey that CBF QP condition with that gamma term. Whereas we approach the boundary of safety, we have to act more safely. So it's just those three terms in the loss function. We take the agent state and the agent obstacle relative states, throw that through an MLP and LSTM, and end up with this barrier function conditioned on the relative state and that history. This is what it looks like. These are the two different steps. This is the initial stage, and this is the refining stage. Here in red is the average path length to the goal, and in blue is the collision rate over training time. For the training and testing setup in simulation and in person, for the simulation environments, the training is performed with 6 human pedestrians using ORCA for the policy. And then for experiments, the training is performed with 2 human pedestrians using grad students. For evaluation, we randomly initialize the robot, human, and goal configurations in denser environments. And if at any point in the trajectory, the robot A collides with a human or cannot find a safe control action, then we consider that full trajectory a failure. So if there's any feasibility issues, we consider that a failure. How we compose this online is the same way as we said before, where every time I see a human, I just slap down one of these barrier functions. And then I say minimize the difference between my desired control and the control that's required to satisfy all the safety constraints. So I'm still treating these completely independently in terms of how I'm reasoning online. So these are the level sets of these functions that were slapped down by the grad student. But where the hope is that in the shape of the function, I am implicitly capturing these interaction effects. These are some baselines that we compared to. First, sampling-based potential field methods. So here we're using potential fields, which are like control barrier functions without dynamics. I have repulsive fields around each obstacle and attractive fields around the goal based on Euclidean distance. In each step, we sample actions and evaluate the predicted next states of those actions. We have a gradient-based version of that, where the control is based on the gradients of the potential field. We compare to a black box multi-agent control barrier function. So this is just using our normal data-driven control barrier function. Here we're using the max pooling layer in order to deal with extra people in the environment. We compare also to a sampling-based model predictive control, where we learn a neural dynamics model and then unroll it online to generate a tree of future states and select the action that leads to the best predicted outcome. And then we also compare it to PPO and DQN. First, let's look at just these three. So here's using a robot that's a double integrator, a bicycle, and a Dubin's car. In blue is our method. In orange and green and red are these appropriate methods. And you see that our method scales, even though we trained in just 6 people, as we go up to 600 people in the same environment, our method tends to avoid collision much better than these other methods. We can keep the collision rate under 10% when scaling to 60 times denser environments. And the collision only reaches 15% in a bicycle model case with a 100-time denser environment than the training. Note that the gap in safety is more significant when the robot has more complicated dynamics, such as the non-holonomic Dubin's car, where actually embedding the dynamics of the robot into the construction of this function is important. Here's kind of an example of where this works well. Here we have a narrow corridor situation where 2 humans are passing by each other. If you're using potential field methods, then just following the gradient directly ends up causing the robot to turn and actually collide. Whereas here, looking at the level sets of the control barrier function, you see that the robot is able to navigate through the space by looking at the history of the agents. So here's with the bicycle and with the car. Note that the CBF that encodes the bicycle dynamics has a wider gap between level sets, aka a steeper gradient, reflecting the need to initiate collision avoidance much farther away from the obstacles because of the dynamics of the system. Okay, let's compare it to MPC. So standard MPC requires the use of analytic dynamics, so both the ego robot and the humans. And so we can't just throw MPC into this without modifying it somewhat. So instead, that's why we find that neural dynamics, and then we roll it out. We sample actions and forward predict the future states, 10 or 100. And then select actions based on the potential field values of those predicted states. And we also consider the case where the sampling-based model predictive control has access to the true dynamics of the human. So we tell it exactly what the humans are going to do and allow it to do MPC. This is in order to get kind of like a baseline, an oracle in a way. Because you can imagine if there's 600 people in a space, perhaps there does not exist a safe path to your goal. So that one where we give the MPC access to what the humans really are doing, this is what the curve looks like there. Here's for the other sampling-based methods, and then here's ours. We think that ours work better here because it does not require multi-step unrolling, and it avoids the accumulation of model prediction errors that are inherent in the learned models of dynamics. Okay, and then finally, there's so many baselines that we compare to because it kept getting rejected from machine learning conferences, so we just kept adding more baselines. So let's do now PPO and DQN. So here again, we train an environment with 6, tested on 600. And we actually, in each of these cases, we use the action produced by PPO or DQN as the nominal action that we want to use in our QP. So we say, try to follow this action and just override it if you need safety. And we're able to deal with denser environments because we made our method better at scaling than just standard training. And then we have a little initial hardware demo. We now moved into our fancy new building, and so I have a lot more room to play around with and all of Henrik's toys. But for the initial one in this small temporary lab space, we had the training with 2 people. Ignore the person carrying the battery. That was just the battery holder. And the robot is trying to get, along this path is what its desired reference is. And then we test this in an environment. More people, note again, because it's a small environment, the people have to kind of move awkwardly around each other. So we really want to do this differently now that we have more room. But so we're trying to follow, again, the same path. And you see that often, like here, the robot has to deviate quite a bit from that path in order to maintain safety with respect to the people. Here, the people were told to look up and not look down at the robot at all and just interact with each other. This is an assumption that we're making in general in order to help with data augmentation, that humans do not react to the robot, which is a silly assumption that we're trying to now tackle. Okay, so in summary, we exploit the important observation that the spatial interaction patterns of multiple obstacles can be decomposed and predicted through sequential modeling of individual obstacles. So we can take spatial interaction and instead encode that as temporal information. We design these models that incorporate sequential modeling of individual obstacles so they can be composed in environments with an arbitrary number of obstacles online. Next, we want to do our larger scale experimental validation and some analysis of the probabilistic safety properties of the methods under certain assumptions on the environments. We just presented this at IROS and actually then won the Robocup Best Paper Award. So I guess keep getting your things rejected from machine learning things, build up all of your baselines, and then submit to robotics. It seems like a pretty good strategy. I don't know. But it turned into a pretty good paper, I think. Oh, and consider other information that we can encode into the control barrier function. Okay, so that's the kind of pitch that I told ONR. That's the things that we have been working on. I want to, again, highlight my PhD students, my undergraduate and master students, and all my collaborators. For this particular project, the green thrust was done by students Jason and Donggun and their advisors Koshal and Claire at Berkeley with me. And then my student Jung did the extension to control Lyapunov functions along with my TA, who is a student of Tom Bewley. For the second one, quickly approximating CBFs and use that for initialization, my students Sander and Alex, who's now at BrainCorp, worked on that along with Sean Gao and his students. Updating these online based on changing assumptions and information. Sander is now guiding a team of undergraduate and master students for doing experiments now that we've moved into our space. And for reducing the conservativeness for unmodeled dynamics, that's work with Sean and his students. And with that, I am done and happy to talk now about questions and comments and concerns. If we don't get to all of these things for you, my email is very easy to remember. It's sherbert or sherbert@ucsd.edu. And with that, I am done. Thank you.
So I hope you'll get some.
What are the steps you have to take, and are there any unique steps you have to take to discretize the CBF HJR sort of formulation that you showed?
For the patching thing?
No, way earlier on, I think it was in the green section or the blue section, you showed the formulation where you included the CBF requirement with the HJR formulation, but that's done in continuous time. When you implement it in hardware,
when you implement it, you do it on a discretized state space. And all of this Hamilton-Jacobi reachability stuff is done ultimately in a discretized state space using dynamic programming because we have digital computers. And so yes, there's a lot, both in space and time, you have to sample finely enough. And there's work on what finely enough means. In fact, if you really want to bother someone, is somewhere, and you should track him down. Yeah.
It's really more of an observation. I thought it was interesting that you were starting to work with real robots because, of course, they do have uncertain sensing. There's noise and so on. And you started to say a little bit how you're dealing with that. And I even noticed in the video that you showed at the end of people walking around. You say, well, two people are walking towards each other. They're going to see each other. But even when there isn't anybody coming towards you, I saw people walking and then just sort of randomly making sharp turns to the left or right. Yeah, I don't know.
Yeah, absolutely. So some of the work that I did in my PhD with Claire and with Anka Dragan was on can you get away with using really dumb models of humans, and when they obey your dumb models, then you have very tight confidence around them, and when they act differently, whatever that means, then you degrade your confidence and end up in the extreme, considering the worst case example. So how do you switch between levels of confidence here? I think we'd be curious to incorporate something like that in here, but there's this trade-off between how much reasoning do you want to do online versus offline? How are you reasoning about uncertainty? Yeah, all of that we're very interested in. The state estimation stuff we're very interested in. There's a project with another TA of mine who now comes to my group meetings who is interested in how do you reason about what is the state that is best to believe you are in order to be robust rather than the state that you are most likely to be in. So we're exploring some things like that, which has been fun and good for me when I've been very much protected in this world of just assuming perfect information, and I'm pushing out of it.
So on a related note, could you share a bit more about how you are considering the human's response to the robot moving around them?
Yes, thank you. So it's been forced upon me because one of my students, Nikhil here, he's co-advised by Mike Yip at UCSD, who's in surgical robotics. And he wants to do safe surgical robotics, which is a crazy hard thing for him to want to do. But so we're starting off with the rubble thing that I showed you before, the Pringle scans, where we say, okay, let's not tug on people's tissue, but let's start with some Pringle scans. You want to try to push them around in order to get to the goal without knocking things over. Where eventually we're hoping to move that towards how do you tug and move around tissue in such a way that you maintain safety while getting towards your goal with the Da Vinci robot. Anyway, he wants to try porting this over onto that situation where now the humans are Pringle scans. And we were very excited about that. And then we realized, Pringle scans do not move independently. Like, they literally will only respond based on actions that you take as the robot. So we actually have to deal with this fact that the humans and robots are interacting. And so in terms of the training itself, it doesn't break too much the process of what we do at a high level, but it does change how we have to gather data. So before we would take some samples of robots and human moving across the lab, and then post-processing we would ask, okay, what if the robot was here or here or here? Would it have remained safe? And by assuming that the humans ignore the robot, we can just use the same recording of the human trajectories and be able to refine our safe set using that. Now we have to actually gather enough data with actually knocking around Pringle scans in order to do that. So we're exploring a few different methods for how to deal with that. And that is very much still in the active exploration side of things. So if people have ideas, I'd love to hear them.
Anything online? No questions.
Okay, perfect. Well, again, if you have any follow-up thoughts, comments, questions, please feel free to reach out to me. And I'm also here for the rest of the day. All right, thanks so much.